Okay, my name is Arif Nyakyuddin bin Sharudin, matric number CD170156. Now I will present about the result of the experiment, which is a boundary layer. For the table 4.2, velocity distribution on a smooth flat plate, the ambient temperature is 23 degrees Celsius. There is 16 reading, and we have to calculate the pressure, which is using the formula rho GH for static and dynamic. First we calculate the dynamic, then subtract the static, and we get the pressure. Then we calculate the air velocity U, which is square root pressure multiplied by 2 and divide by the air density. After that, we calculate the velocity ratio, which is a square root the P, pressure, divide by the maximum pressure. Then after that, we calculate the 1 minus velocity ratio, which is 1 minus the result of the velocity ratio, and we repeat that for 16 times. As you can see on the table, the result of the experiment. Then after that, we calculate the table 4.2 for velocity distribution on a rough flat plate. Same formula we use. First we calculate the pressure, which is using rho GH for dynamic, then rho GH for static, then subtract together dynamic, subtract the static. Then we calculate air velocity U, then velocity ratio, and 1 minus velocity ratio. Same as table 4.1, there's a 16 reading, but the only difference is the micrometer reading and the manometer reading. After that, we complete the table, and that's all. Thank you.
Okay, my name is Muhammad Hamidullah Master. My number is CD170115. So I want to present about the observation. So from the experiment, it shows that the manometer level will increase if the paper tube moves to right, or in other words, it moves out. When the paper tube reading is increased, the manometer becomes faster. To increase parallel error can damage and affect the result if not read the manometer level carefully. From the data, the graph travels this distance y against velocity ratio in smooth plate shows the increasing in data. The graph travels distance y against velocity ratio in rough plate shows the data is increased. So the graph travels distance y against u over u. The smooth plate shows decreasing in the graph. In the rough plate also shows decreasing in the graph. That's all. Thank you.
Hello, my name is Harite Sekai, and I'm from Group 5A. So today I will discuss about the calculations for topic 4, which is boundary layer. So for the first question is calculate the displacement thickness, momentum thickness based on the graph that has been presented by my friend, and then calculate the shape factor. So first I will refer to the smooth flat plate. From the graph, when y1 is equal to 0.2 millimeter, the velocity ratio is equal to 0.728. When y2 is equal to 5.5 millimeter, the velocity ratio is equal to 0.993. Next, we need to find h, where we use the formula velocity ratio 2 minus velocity ratio 1 divided by 2, and we get 0.1325. Then we find the center, which is the sum of the velocity ratio of both of 1 and 2, and divide by 2, we get 0.861. Then in order to find the velocity ratio for the whole line, we use a formula, which is this one, h over 3 multiplied by the sum of velocity 1 plus 4 times center plus 2 times the velocity 2, and we get 0.272. From here we can find the displacement thickness, which is 1 minus velocity ratio of this 0.272, and we get 0.728. Next, we need to find the momentum thickness. The steps are more or less same as the previous one, just the difference is when y1 is 0.2 millimeter, we need to use this formula, the velocity ratio multiplied by 1 minus velocity ratio, we will get 0.198. For y2, we will get 0.07. So same steps, we find h, find the center, which is 0.096 and 0.1025. We can find the momentum thickness data. Same formula as this previous one, and we get 0.0299. From here we can find the shape factor h, which is we're using the formula displacement thickness over the momentum thickness, and we will get 24.35. Next is for the rough flat plate. Same steps. When y1 equal to 0.2 millimeter, the velocity will be 0.582. When y2 is equal to 6 millimeter, the velocity ratio will be 0.970. Sorry. And we find h will be 0.194. The center will be 0.776, and we get the velocity ratio of 0.364. And then we can find the displacement thickness, and the value is 0.636. And next, we need to same steps as the smooth flat plate, find the momentum thickness, and then we find the shape factor h, which is the formula of displacement thickness over momentum thickness. We get 21.13. Next, the questions is about the calculate theoretical value of displacement thickness, momentum thickness, and shape factor. Here we need to find the value of these three by theoretically. So the temperature they have give is from the module is 23 degrees Celsius. So we add by 273 will become 296 Kelvin. So since we cannot find the value of V, so we need to use the method, which is the interpolations. After interpolation, we will get the value of V 1.3532 times 10 power negative 5 meters square per second. And from this, we'll get the Reynolds number for smooth flat plate and the rough flat plate, which is 19.719 times 10 power of 3 and 19.235 times 10 power of 3. So since the Reynolds number, both of these is more than 4,000, so these are considered as turbulent flow. So next, from here, we can find all of the three displacement thickness, momentum thickness, and shape factor for smooth flat surface and rough flat surface. Next is the calculation in order to fill in the missing part from the result, the table. So there are total of 5 calculations we need to count, which is the pressure. We need to find the air velocity, the velocity ratio, the 1 minus velocity ratio, and this one. So before we find all these values, first we need to know the density, the air density. So for the formula for the air density is the atmospheric pressure divided by the gas constant multiplied by the ambient temperature. From the module, they have give the value of atmospheric pressure, which is 1.01 times 10 power of 5 Newton per meter square. For the ambient temperature, as I have said before, it is 296 Kelvin, and R is a gas constant, which is 287.2 joule per kilo Kelvin. So from here we can substitute all the value inside the formula, and we get the air density of 1.188 kilometer per meter cube. So now we will calculate the pressure first, which is the dynamic pressure minus static pressure. We can convert the pressure into rho GH, substitute all the number inside, and we will get the answer of 353.16 Newton per meter square. And B, we'll need to find the air velocity with the formula of square root 2p over air density. Substitute the value inside, and we will get 24.38 meter per second. Next, we'll find the velocity ratio for smooth flat plate, which is we're using the formula of square root p over p max. P max we can get from the result table, where we choose the highest pressure that we have obtained from the experiment. So from here we will get the answer of 0.728. Next, 1 minus velocity ratio, we will get 0.272. And lastly, the velocity ratio times 1 minus velocity ratio will get 0.198. Same steps as the previous one from the smooth flat plate. This is the example of the rough flat plate. So the density of air we have been calculated before, which is 1.118, and we will get the answer here, which is pressure is equal to 225.63 Newton per meter square. Air velocity is equal to 19.49 meter per second. The velocity ratio is equal to 0.582. Next is 0.418 and 0.243. And all of these value are from the example calculation for the row number 1, the number 1. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Faiz Nur Ashraf bin Hassan. I'm going to talk about discussion of the topic boundary layer. First, compare and discuss the result of theoretical and experimental values. So the result of theoretical and experimental values was they have different value, which was very high. This is because there were experimental error occurred which affected the value in the experiment. Second, for the rough plate, the velocity distribution does not fall towards zero at y equals 0. State the reason and method to solve this problem. For the rough plate at y equals 0, rational flow occurs outside when the flow through the rough surface. The reason is flow outside is not the same with the flow inside. To solve this problem, we can use the momentum integral method. Third, explain the effect of surface condition on the formation of boundary layer. The effect toward the surface condition are the force which acts toward the surface, which is the friction and viscosity force formed from air velocity. When the velocity adjacent to a surface, the value of u, which is the value of which touching the surface, will be static and cause the forming of the boundary layer. Fourth, predict the result if the liners on the test section is reversed. Becomes accelerating flow. What would happen? The air particles will have high pressure and the flow will become more faster. The boundary layer will grow more rapidly and the shape vector increases, and the pressure rises in the direction of the flow. Last, fifth, state at least 5 sources of error in the experiment. The manometer level is not stable, so that it is difficult to get its accurate value. We thought tube was not touching the flat plate properly. Parallax error occurred while taking the reading for both manometer and micrometer. The position of mercury level did not stabilize when having a pressure which caused the exact reading hard to get. And the airflow is not constant and cause air wave to occur.
Okay, now I want to explain about the conclusion. So from this experiment, we can understand the concept of fluid flow past a flat plate through a region called the boundary layer. We are also able to relate the effect of smooth and rough surface of the plate to the formation of the boundary layer. Instead, we must measure the velocity distribution, displacement thickness, and momentum thickness in boundary layer of a flat plate. We must compare the value measured for both smooth and rough plate installed with a pressure gradient. The objective in this experiment is achieved when the result is shown that the displacement thickness and momentum thickness for the rough plate or surface highly than smooth surface, so that the boundary layer is influenced by the surface condition while the motion through that surface. The formatting of boundary layer also based on the friction which is action to the surface. That's all from me. Thank you.